Alright, so we have arrived at what is probably the entire point of this course, which is starting to manage composite functions. So before we start, this function I'm going to go through is the very first one in the practice problems. So you might want to print those out first, or get them however you get them, and then sort of follow along and fill out the sheet as we go. I'm going to try and stick to the analysis on that page in the order that it's presented, so that you can use it as a model to do the rest of the sheet. So I have this multiplication type composite here, right? I can see that there is a radical multiplying a parabola. So the very first thing in the analysis says write that as two separate pieces. So I have this x plus 5, and I have this x squared minus 4. So those are the two things that I'm going to have to think about. And the idea here is that the features of this one are going to show up in this composite when I'm done, or some of them will, because it's one of the ingredients. The features of this thing are going to show up in this composite as well, because it's one of the ingredients. Sometimes the features fight, and we're going to have to work that out. Sometimes they complement each other, and we're going to have to work that out. But for now, just start by splitting them into the two separate things. Part B, determine the X and Y intercepts of each piece. Okay, so this X intercepts first. So I'm going to set this to 0, square root of x plus 5. Square both sides, I get 0 equals x plus 5, so I get x is negative 5. This one, 0 is x squared minus 4, so 4 is equal to x squared, so plus or minus 2 is x. So I found all my x-intercepts. Now I'm going to get my y-intercepts. So when just putting 0 in for x, so square root of 0 plus 5 is root 5, which is approximately 0.2, I think. Square root of 5, 2.24. And here, if I put a 0 in, I'd have 0 squared minus 4, which is negative 4. So I've gone through, and I found the first feature I need in order to do my analysis. I have my x-intercepts in this box, and I have my y-intercepts in this box. Lovely. Continuing on, do either of the pieces have boundary errors, which is another way of phrasing vertical asymptotes? So this is a radical. Radicals look like this without an asymptote. This is a parabola. Parabolas look like this without an asymptote. So the answer to that particular section would be no. There are no boundary errors. Okay, so the point of asking that question is if this thing doesn't have a vertical asymptote and this thing doesn't have a vertical asymptote, then this thing, which is a combination of those two functions, can't have asymptotes either, right? You can't put eggs and milk in a bowl and end up with horses, right? It's not an option. If you don't have this particular ingredient in the mix, then it won't show up in your final function. All right, on to the next one. Do either of the pieces have a domain error? And so domain error is a place where that particular piece doesn't show up. Parabolas don't, but a radical does, right? A radical starts at a particular place and takes off. So just looking at this, I know that any x value less than negative 5 doesn't work for this function. So there is a domain error. For x less than negative 5. Negative 5 is okay, right? Negative 5 plus 5 would be 0. Square root of 0 has an answer, but anything less than that doesn't actually work. So identified those things. All right, and the next part says sketch the two pieces on a grid. So I'm just going to do a very rough sketch so that you can see approximately what they look like. All right, so that radical piece, 1, 2, 3, 4, 5, starts there, and then over 1, up 1, over 1, 2, 3, 4 would be up 2, 5, 6, 7, 4, 5, 6, 7, 8, 9 would be up at 3. So it's something like this. Wow, that's better. All right. Now this piece here, the parabola, that's a parabola that's been shifted 4 down. So 4, then over 1, up 1, over 2, up 4, over 3, up 9, something like that. Okay, good. I managed to throw my calculator and all of my markers on the floor here, so let me gather myself. Great, good. On to part F. Will any of the features you identified be erased by a domain error? If yes, list them. So this parabola keeps going upwards. And once it gets to this domain error, it's going to stop. Did you notice that its x-intercepts are safe because they're not over there? Its y-intercept is safe, it's not over there. Didn't have any asymptotes anyway. So really, I'm just going to lose this left branch of that parabola. It's going to get cut off by this domain error. So if I make a little statement about that, the domain error will clip the parabola below x is -5. Okay, good. So G, is there any place where the x-intercept of one piece falls on the boundary error of another? Well, I don't have boundary errors in this particular function, so the answer to that is no. No overlap of x-intercepts and boundary errors. All right, part G. Oh wait, we just did that. Part H. Use logic, patterns, or the limit as x goes to plus or minus infinity to determine the end behaviors of this function. Okay. So as x goes to positive infinity, so if I'm coming out here, this branch, this radical, gets bigger and bigger and bigger and bigger as it goes along. This parabola gets bigger and bigger and bigger as it goes along. So if this is getting bigger and this is getting bigger, then you multiply them together, you're going to end up with something much bigger than either of them on their own. So this thing goes to infinity already. This thing also goes to infinity. So as this thing goes out to infinity this way, it's also going to be taken off. So I don't have to do any math for that. I can just write it down. As x goes to positive infinity, f of x goes to positive infinity. Now, on the other end, so I'm trying to go to x equals negative infinity over there, and as soon as I pass 5, I end up in a domain error. So it actually doesn't exist over there. So as x equals negative infinity, I mean goes to -5, because that's really the end. Well, what's happening in this place? Well, at this particular spot, I have an x-intercept, so this is worth nothing. This is worth -5, 25 minus 4 is 21. What's 0 times 21? Well, it's 0. So as x goes to -5, the function goes to nothing. Okay. Good. So I've got all the major features listed on there. Now the next step there is take a deep breath and boldly attempt a sketch of the full composite function. Now you can't actually nail this without calculus, but we're going to take a stab at it and just come up with something that's approximately correct and that captures as many of these features as we possibly can. So I'm going to grab my grid here. Alright, I'm going to put on an X and a Y axis. Alright, so first things first. As I pointed out in this particular line, when I'm at -5, which happens to be an x-intercept of this thing, it zeroes out the whole function. That's going to happen at every x-intercept, right? When I go to -2, put -2 here, this is worth nothing, and this is worth √3. Well, 0 times √3 is 0. So I'm going to take all of these x-intercepts. Every x-intercept of each piece ends up being an x-intercept of this function in a multiplication type composite. So I need one at -5. 1, 2, 3, 4, 5. I need one at -2. And I need one at +2. That's there. Okay, my y-intercepts. These are on here primarily to help me sketch these two bits. I could get my y-intercept by taking the y-intercept of this one and multiplying it by the y-intercept of that one. Basically, I'm just putting 0 into the function here and working out the mess. So I end up with √5 times -4 is going to be -8.96. Yeah, -8.94. So I have to find -8.94. 1, 2, 3, 4, 5, 6, 7, 8, 9. Somewhere in about here. I don't have any asymptotes to deal with, but I do have to remind myself to not draw anything past here. So, the void. Right here be dragons. Don't go over there. Okay. Good. Maybe just put in a little. Don't go past this spot. Alright, the domain error will clip the parabola below x less than -5. Well, we got that. No overlap of x-intercepts and boundary errors, so all three of these x-intercepts are going to show up. As x goes to +infinity, this thing should be taken off. So maybe I'll just put a little like, go that way. Lovely. And as x goes to -infinity, I mean as x goes to -5, I am approaching 0. Okay. Good. Now here's where a little bit of work starts happening. I need to fill in a few dots in order to get approximately what the height is. And the trick here is that this function is a piece multiplied by a piece. So if you know the y value at a particular place of this one, and you know the y value of this one at that same particular place, you can get the y value of the full function by just multiplying them together. So I'm going to start with this spot here. This is at 1, 2, 3 at -4. So if this was -4, I'd have 16. 16 minus 4 would be 12. So the parabola is 12 high, and my radical is 1 high. 1 times 12 would be 12. So at that same place, -4, I'm up at 12. 11, 12. All right. Next place over, I have 1, 2, 3. My parabola, 3 squared would be 9. 9 minus 4 would be 5. This is worth 5. And at -3, this would be worth the square root of 2. So the square root of 2 multiplied by 5. 5 root 2 gives me 7.07. So at -3, I should be at 1, 2, 3, 4, 5, 6, 7 and a bit. And then the next one over is the x-intercept of this particular parabola. So I'm going to be able to just sort of sketch this in here. Up she goes, down she goes. Something like that. Next line over at -1. At -1, this thing is at -3. And at -1, this thing is at 2. So -3 times 2 would be at -6. 1, 2, 3, 4, 5. That'd be here. I already have 0. That's at the y-intercept. Next spot over at 1. 1 squared minus 4, that's worth -3. 1 plus 5 is 6. So the square root of 6. -3 times the square root of 6 is 7.34, -7.34. So 1, 2, 3, 4, 5, 6, 7 and a bit. At +2, I'm back at an x-intercept, so I can sketch this thing in here down to this point, through the y-intercept, back up. I could do a few more. I'm going to skip until I get another nice clean value on this parabola or the radical. So that doesn't happen until 1, 2, 3, 4, 5, 1, 2, 3, until x is 4. 4 squared would be 16 minus 12. This would be 9. So square root would be 3. 3 times 12 is 36. Remember that thing where f of x got really big as x went to infinity? And I've got this little arrow reminding me. Once I've gotten through all the features, I might as well just follow the end behavior. So, sure, that'll do. So I get this neat little function that does something like that. Now, if I were to zoom out a little bit, because that looks kind of like a cubic, but it's not. This function does a little bounce, and then it takes off. Kind of like a check mark. It's kind of fun. So I can see the domain error of the radical function clipping it off over here. And then I can see the parabola taking off. It probably takes off more like this. Alright, lovely. So I went through the analysis, I answered all the questions, and I was able to spit out something like this. And again, this isn't exactly right, but if you were to dump it in Desmos and have it sketch it on the website, type this stuff in. If you can get it typed in correctly, you're going to get a function that looks more or less like that. So I'm going to erase this, and we're going to try one that's a little more complicated, and then I think you're good for the practice problems. Okay, so we're going to try one that has a cosine in it and a rational expression. This is the basic rational, just 1 over x. So back to the analysis, same questions. Write f of x as 2 separate pieces. So my separate pieces then are this rational with an a value of 4 and a cosine with a leftward shift of pi over 2. Alright, so determine the x and y intercepts of each piece. So this particular thing, if I set this equal to 0, I get a fail. If I put a 0 in for that, I get a fail. If you remember what the rational looks like, it doesn't actually pass the x or the y axis. So there are no intercepts for this one. This one, if I put in 0, I end up with cos of pi over 2. And the cosine of pi over 2 is 0. So I have an x and y intercept at x equals 0. X-intercepts, I set that thing equal to 0, pi over 2, arc cos both sides. Cosine is worth 0 at pi over 2 plus 2 pi n, and at 3 pi over 2 plus 2 pi n. And so if that's equal to x plus pi over 2, and so is this, subtract pi over 2 from both sides, I get x is 2 pi n, and here I get x is pi over 2 minus 3 pi over 2 is minus pi plus 2 pi n. Okay, so this would be 0, 2 pi, 4 pi, 6 pi, etc. This would be 0 pi minus 1 would be minus a pi. 2 pi minus 1 would be 1 pi. 4 pi minus 1 would be 3 pi. Do you notice that I have minus pi, 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi? It's all the pi's. So I'm going to erase this and I'm going to write that in as all the pi's. Alright, good. So I've gone through and I found that there are no x-intercepts there. That's the y-intercept for that one, and then all the pi's are my x-intercepts for the cosine. Okay, good. Part 2. Do either of the pieces have boundary errors, which are vertical asymptotes? This one does. This one has a boundary error. Boundary error. When x equals 0. Okay. Do either of the pieces have domain errors, so places where the function doesn't show up? This one only has the boundary error. Once it gets by that vertical asymptote, it slowly decays to nothing on one side and slowly decays to nothing on the other. There's no boundary errors there. Cosine, or domain errors, sorry. Cosine doesn't have errors at all, so I don't. The answer for D would be no domain errors. Okay. And sketch the two pieces on the grid. So if I just draw in a cheap little x and y axis. Now cosine wibble wobbles between 1 and negative 1. And it's been shifted pi over 2 to the left. Pi over 2, 3.14 divided by 2 is about 1.5. So that's 1. That's about here. And then it's going to repeat, because it doesn't have a k value in it, it's going to repeat every 2 pi units. 2 pi is about 6. So 1.5. And another 1.5, 1.5. So 1.5, 1.5, 1.5, 1.5. So this cosine peaks, then hits 0, then troughs, then returns to 0, then peaks again. And then it repeats that over and over and over again. Etc. Alright, now this rational function, it has an a value of 4. So instead of over 1, down 1, it'll be over 1, down 4. Pink here is taking a vacation. 1, 2, 3, 4. 1, 2, 3, 4. So this will be that and like that, and then it has this decay to it along the x-axis, something like that. Alright, good. On to question F. Will any of the features you identified be erased by a domain error? Well, there is no domain error, so no, that's not going to happen. No domain error issues. Smiley face. Or maybe frowny face, because you were excited for domain error issues. Question G. Is there any place where the x-intercept of one piece falls on the boundary error of another? Well, I have an x-intercept at 0 and a boundary error at 0, so that's problematic. I have an x-int on an asymptote at x equals 0. If yes, take the limit of f of x as x approaches that place to determine which feature wins. Okay, so I'm going to do 0.1, x equals 0.01, and x equals 0.001. And we're going to see what happens. Alright, so I'm going to do this piece for each of those values. So 4 divided by 0.1 equals 40. And so this will be 400, and this will be 4,000. The cosine part, to make sure I'm in radians, 0.1 plus pi over 2 gives me 1.6707, something. Cosine of that is negative 0.99833. Right, and for this one, 0.01 plus pi over 2 is 1.58. Cosine of that answer gives me negative 0.00, and then a whole bunch of 9s. 0.001 plus pi over 2 equals 1.5717, and the cosine of that gives me 0.0009999. So if you look, this thing is approaching infinity, right? The rational is getting bigger and bigger and bigger as x goes to 0. The cosine, on the other hand, is getting smaller and smaller and smaller. So I'm going to have to go through and I'm going to have to figure out what the trend is here. So the product of those two things, 40 times 0.09983 is 3.9932. Here, 400 times 0.0999 gives me 39.96. Oop, 3.96. Hold on, I need to get the exact value of this. 0.01 plus pi over 2 cosine times 400 equals negative 3.99993. And for this one, 0.001 plus pi over 2 equals cosine of that times 4,000 equals negative 3.999999933. So if I take a look at this, as my x values are getting closer and closer to 0, it looks like these numbers are getting ever closer to negative 4. So as x approaches 0, this function is approaching negative 4. Alright. Now I want to check that coming from the other side just to make sure that it matches up. So I'm going to repeat this calculation here for negatives, and I'm just going to use this. I'm just going to use this space so I don't have to write everything down again. If I make those x's negative, then my rational function pieces just become negative as well. I'm going to check the cosine then. So negative 0.1 plus pi over 2 is 1.4707. Cosine of that equals 0.0998334. Okay, I'm getting the same value, but instead of being negative, they're coming up positive. Alright, lovely. Which means that this is going to be positive. No, it won't. Negative times a positive is a negative. So it looks like as x comes to 0 from both sides, this thing is going to negative 4, which is kind of neat. So what happened there was this asymptote from the rational and the x-intercept from the cosine ended up neutralizing each other. And so I end up with the value showing up at a finite spot on the graph, but not at the x-intercept. So I've created a little punch hole at that particular place. All right. So using logic, patterns, or the limit of x goes to infinity to determine the end behaviors of the function. Okay. So this is a multiplication. I'm going to take the height of this cosine, I'm going to multiply it by the height of that asymptote. Now this cosine just wibble wobbles back and forth between 1 and minus 1, 1 and minus 1. So the biggest it gets is 1. As this thing goes out, it decays away to nothing. So when I choose a big X, like 10 or 100, this is worth nothing and this is worth 1 at most. So 0 times 1 would be nothing. On the other end, this is also decaying to nothing, and this is wibble-wobbling back and forth between 1. So a piece that decays to nothing multiplied by a piece that is at most 1 isn't worth anything either. So as x goes to positive infinity, f of x goes to 0. And as x goes to negative infinity, f of x also goes to 0. Okay. So I guess the last thing then is to take a deep breath and boldly attempt to sketch it. Alright, so I'll get myself an x-axis. And a y-axis. I'm going to go through and try and put on these features. So I had no intercepts from this piece, but I had intercepts at all the pi's for this one. So pi is at a little bit more than 3, and a little bit more than 6, and a little bit more than 9. Same thing in the opposite direction, negative pi, negative 2 pi, negative 3 pi. Alright. This boundary error and this x-intercept in the center ended up collapsing on each other to create this hole when x is 0 and y is negative 4. So I'm going to draw that hole right there, like so. And as x goes to infinity, this is dropping away to nothing, so I'll just give myself a little arrow there, on both sides. Okay. So I'm going to go through and I'm going to use the peaks and the troughs of the cosine to try and figure out the heights of these particular functions. So at this peak, which happens at pi over 2 is about 1.5. This thing is 4 divided by pi over 2. Now we're just approximating. So this place here, where this peak lands on that, I have 4 over negative 1.5 multiplied by a peak here. Well, that's 1. So whatever 4 divided by negative 1.5 is going to be the height of my function here. So 4 divided by 1.5 gives me negative 2.67. So at pi over 2, which is approximately 1.5, I'm down at 2.7-ish. On this one over here, this happens at positive pi over 2, and at positive pi over 2, this thing would be worth 4 over 1.5, because pi over 2 is approximately 1.5. And then this is at negative 1, because it's a trough. Well, this will be the same value, right? Because the numbers are the same. So you can try it. 4 divided by 1.5 is 2.667 times 1 is negative 2.667. So I've got this thing here. Next peak happens at 3 pi over 2. So 3 pi over 2, let me just figure that out. 3 pi divided by 2 is approximately 4.7. So at this trough, the cosine is worth negative 1, and this would be 4 divided by 4.7. On this side, it's a peak at 3 pi over 2, and 3 pi over 2 is approximately 4.7. So whatever 4 divided by 4.7 is, end up with 0.849. So on this side it will be negative. It's negative that, positive that. So negative times a negative is a positive at 0.848. Pi over 2 is here. And on this side, it's the same thing. Positive, yep, positive times positive. Be about like that. And the next spot I've got out here is 1, 2, 3, 4 is 5 pi over 2. So 5 times pi divided by 2 is about 7.85. So on this side it's negative 7.85. On this side it's positive 7.85. On this side at 5 pi over 2, that's 1, 2, 3, 4, 5. I've got a peak, so that's a positive. On this side I have 1, 2, 3, 4, 5. I'd be at a trough, so that would be negative. So notice I'm getting both negatives. Notice this thing is very symmetrical, right? Cosine, that's a feature of cosine. So 4 divided by 7.85 is 0.5. So on this side I'm at half over here. Do you see how these peaks are shrinking? So if I were to try and sketch this in, I get something that looks kind of like this. Do you notice how the peaks of these things are slowly vanishing? So, I mean, that's our approximate function. And if you want pop it into Desmos, you'll get something that looks approximately like that. It may not be exactly, but it'll be close. The other way I want you to try and think about this is out here in front, we sketched functions all the time like this if they had just a number, right? Like if this said 5, you knew the amplitude of that cosine was 5. If it said 2, then the amplitude of that cosine was 2. This number out here, though, it's not a solid number anymore. Now it's a function. But it's still sitting in the slot where your a value should be, which means that this function, this rational, the decaying rational, is acting like the amplitude of this cosine. So if you look, the amplitude of this wave as I go is shrinking like that rational function does. Same thing on this side. And if I were to even try and dot it in here for you in yellow, 4 divided by 2 is 2, 4 divided by 3 doesn't work, 4 divided by 4 is 1, 4 divided by 1, 2, 3, 4, 5, 6, 7, 8 is a half. If I take this, the normal rational, and then I do a reflection of it, because the cosine flips back and forth between positive and negative, I need both sides as the boundary. But if I draw that in there, you notice how the cosine stays nicely trapped between those arms on both sides. And so then when this happens, as x goes to infinity on this side, the gap within which that cosine gets to wibble wobble eventually shrinks away to nothing, which will take the function to 0. On this side, that gap again shrinks away to nothing, which is going to bring the function down to 0. So we've accomplished all of our features up there with this little graph. Now, I know this is a lot. It is quite a jump from this to this from the rational functions analysis, but as it says in the instructions, take a deep breath and boldly attempt to sketch. The expectation here isn't that you nail it. It's that you can get a rough idea of what sort of features will show up. Sometimes the features cancel each other out. X-intercepts should transfer from each piece unless they are masked. Asymptotes should show up from each piece as long as they aren't masked. Sometimes, if there's masking, you have to take limits. This is all very similar to the rational. So give it a try, see how it goes. Take a deep breath and make a bold attempt, and